Okay, so today's problem is 160 intersection of two linked lists. Um, Basically, I recorded solution 40 minutes ago, but it was like broken. So let me record it again. So we have intersection of two linked lists, and we have two lists as the input, and we need to figure out if they intersect, if there is a common list node from which they start to use the same nodes. So my approach there was mm, to take this node and let's say if we have copy image, can we just paste it here? Paste. Okay, we can paste it. That I didn't know. Okay. Share it here. So my idea is to have like two pointers pointing to the A1 and pointing to the B1, and then move one pointer at a time, and let's have a set A, and initial set A gonna have like empty elements, and then set B gonna be have like empty elements, and then every time we move, we need to check after the move if the new node if the new node that we moved included in the opposite is included in opposite set. If not included, it means that uh, we add it to the current set. If it's included, it means like it's basically first occurrence means intersection. So in this case, we move from A1 to A2, we add A1 to set A. Before that, we checked if set B includes A1. No, it doesn't include it, so it was empty. So I moved it. Next one, we switch the side, we check the pointer B1. If the B1 is included in set A, no. Then we add B1 to the set B and we move the pointer. Let's have this one. Okay, B1 and B1. Let's also say set B equals B1, and we move the pointer. Next, we check the A pointer. If the A2 included in set B, no. Then we add A2 to set A and we move the pointer. Next one, we check B2. If B2 is included set A. Set A. No, it's not included, so we add B2 to the set B. And then we have C2, C1. If the C1 is included in set B, no, we added C1 and then we move the pointer. We moved the pointer, we added that, we moved the pointer to B3. Then we check if B3 is includes set A. No. So we add B3 to the set B and we move the pointer. Next, we check if C2 is included in set B. No. We include C2 into set A and we move the pointer. Ah, no. We move the pointer. And then we check if C1 is including CA, set A. Yes, it's included. It's right over here. So it means that we stop our iteration and we should return C1. So let's assume we had also in this situation like B0 initially. So that would be like uh, B0 and we moved the pointer here. So let's assume we have a pointer C3 at C3. So we check if the C3 is included in set B. No, we added C3 and then we move the pointer. Next time, so it's gonna pointing to null. Next time we're gonna check the pointer. We check if it's pointing to null. If it's pointing to null, we need to skip it because it might be the situation when we have a pretty short um, list A that's pointing to the end of the of list B. So let's say this is list B, this is list A, and then let's say we have like this one. This one is pointing to the last one. In this case, the pointer to the list of list A will belong pointing to the null, but we still need to go to the end of the list B until we see that it's actually it's included into the set A. So let me quickly program the solution. So let's assume we have this one, Java. So for this problem, let's pretend we don't have this one. For this problem, we have um, this function, and then we have a list node like this one, and then what I wanna do, I wanna hash import, make it import Java util hash set, and then we have hash set list node set A equals new hash set hash set list node set B equals new hash set, and then we do the following. Let's say we have list node car A equals head A, and then list node car B equals head B, and then while car A not equal null or car B not equal null, I wanna do the following. If car A not equal null, I wanna do if set A if set A doesn't contains car A. If it doesn't contains, I wanna do set A add car A, and then I wanna car A equals car A next. Otherwise, I wanna so if set A if set B if set B contains car A, it means that car A is intersection and we need to return it. If car, we do the same for the car B, not equal null, and if set set A contains car B, if it doesn't contain, we do set B add car B, and then car B equals car B next. Otherwise, we need to just return car B. And then in the end, if we went to if we have like the same length of the list A and list B, and we didn't find and they don't have intersection, we just will exit the while loop and then return null. So that's it. Let me quickly check if there are any typos. Yep, there are no typos here. Let's check. Okay, so the 12th minute. The next complication here, the follow-up, is to figure out how to do that in of1 memory. So current algorithm, because we have hash set A and set B, we basically save the both lists in a set. We save all the list nodes in a set if we have like had list A length n and list B length m. So the space complexity gonna be O of n plus m, and the time complexity gonna be O of n plus m. So the time of n plus, let's say n plus m, and then space of n plus m. The question is how we can improve this. I've been thinking about this for a couple minutes, and the first idea the first try I want to test it. Maybe I can do some kind of, if I have like either any like reason to have a fast and slow pointer. Let's say we have fast pointer. So generally speaking, I can like go one step for the list B, and then I can go one step for the list A. Then I can go 2 steps for the list A, and then 3 steps for the list A, and then 10 steps for the list A. So the number of nodes there, 10 to the power of number of nodes 3 to the power 3 by 10 to the power of 4 number of nodes. So if I'm gonna always try the same kind of, so like I step one step for the list A, list B, let's say, and I do like list A one step, and let's do like walk it like until the end. Okay, so if I gonna walk, if I wanna walk to the end for the list A and I wanna walk to the end for the list B, they're gonna, if they if they kind of have the same, if they like converge, they will have the same, um, how to say, the same tail. And the problem is that how to actually figure out. So I can like figure out like what has list A or list B the length of it. So I can save the length until I reach the tail for A, and I can get the length for the B. And then if I gonna okay, so basically what I'll do, uh if I move the point of like start the slow pointer from the B and go with it one at a time, and yeah, if I go like slow pointer at the B, and I go like fast pointer at A, and let's say we go like 2 nodes for the A. Let's say this one goes like we went like 1, and then A goes like A pointer goes 1 and 9. Then we go like, let's say we have like extended here 191. Let's say we have A1, A2, A3, A4, A5. Um, let's wipe it. So let's say you have B1 and then merge into C1 and then C2, C3. And then let's say we have like pointer, fast pointer, so B1 and slow pointer. And fast pointer goes on the longer path, and the slow pointer goes on shorter path. Short. So like I have a pointer here, like initially like jumps 2 nodes. So like from this one, 2, and the slow pointer jumps from this one to this one. And then again, we have fast pointer jumps one node, and then another one, and the slow pointer jumps for just one node, and they meet. And the number of nodes they went, so let's say is x, and this one is y, and this one is like z. So we know that this one made like two jumps, two hops. So y plus z equals 2. And then this one did like, so here we don't know y and we don't know z. And this one did 1, 2, 3, 4, 4, 4 hops, and they met. So it's x plus z. And then I need, based on this equation, I need to find like what was the like either z or x or y. I know also that there is a certain condition, let's say, if I divide, okay, so it's like obvious, if I divide 1 by the second I'm gonna have like 2. Mm. Interesting, so are there any other ways I can figure out? So I know that 4 and I know there's 2. How I can figure out like x or y or z? I wonder if I can modify the list. So if I would be able to modify the list, I would just if I can modify the list, okay. Let's assume I can modify the list. So every time I go through the I go through the longer path, and what I do, I No, even like this one. Even okay, so I go with the first pointer and change the value to minus there. Can I use a negative there? So if I change there the first one, let's say I do the following, I change to minus, 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 or like every time I go with the first pointer, I change it to minus, minus, and then every time I go with this pointer, I check if it's negative. If it's negative, so I went through until the end for the first kind of pointer will end go to the end, and the second one will start after that and will go and until it finds the first negative, and then we should go with the second pointer, the first pointer again, change it to positives. Kind of that's one solution. I wonder if it can be negative. Can it be negative? No, it can't be negative. So do this. So let's say we have had carry. While carry not equal null, we do this carry while equals multiplied by -1, then carry equals carry next, and then we do um, while, okay, let's note car b equals head b, and then we do while car b not equal null, we do that car b, we check if car b well equals less than 0. If yes, then we do that with node output equals null, and then we save it, and then I save it output equals car b, and then we do that again and we change it to the, and then we do the break, and then we do the third loop and we change it again, and we return the output. So this will change the space, so it's going to be n plus m time complexity, and the space complexity is going to be O of 1. Check this one. Mm. Okay. Even if car A check if it's compiles. Okay, compiled. Hmm. Okay. Otherwise, car B equals car B next. Okay, that's a little bit better for memory. I wonder if there are any kind of better approach for this problem. I was thinking about turtle and hare solution, but as of now, I cannot figure out like how to do this in this setup. Are there any third solution here? Third equation. So I'll try to do this walk. I go to the end, I can count the number of nodes. So here. And I also know the number of nodes like here. So of one time space complexity, of one space complexity, how to do that? Might be too hard. So this one was A1, A2, AC, C1, C2, C3, B1. So let's say I assumed here that they're gonna meet in this point. But that can, but actually that may not be true. So let's assume they met at this point, like some kind of. Let me check. So we have like this, like this, like this, like this, and we have like this, like this, like this, and they meet, and this then goes so on and so forth. So if I start a fast pointer on the longest branch, this is A and this is B. If I'll go the 2x space here, so like second pointer here, first pointer here, like fast pointer here, slow pointer here, fast pointer here, slow pointer here, fast pointer here, and like we already bypassed. Okay. If you go back and forth, that will still like if I'll go like every time like I go one. I wonder if I should do like the binary search for the like let's say this length is 0, 1, 2, 3, 4, 5, 6, 7. So the length is like 7, and here like it's like 0, 1, 2, 3, 4, 5, 6, and here like length 6. If I say the delta is basically is 1, so I do the binary search between like 1 and 1, and let's say I start at this one, and I start here at this one, and we move in parallel, and we figure out like on next move it's gonna be like okay. But if the this one is like much longer, let's say we have like say -1, have -2, so here we have length 9 and here length 6. So if I start like, or it might be the situation like, yeah, okay. So like if I do the binary search for this delta, and like say, oh, okay, so the idea is the following. The idea is the following. I figure out the length of this longest. I figure out the length of this shortest, and then uh, I subtract from each other like length long minus length short, and I go like in this case 9 minus 6. 9 minus 6 equals um, 3. So if I start from 0, 1, 2, 3 from the third node, and here I start from the first node, like first node, and I do like move them in parallel, um, I will find this node eventually, intersection node. Okay. So let it be. Let's try to do this. I didn't like this solution because we are changing the value to -1, and that's not always possible. What if they say, okay, this one can be, we cannot change the values, or like they are throwing out our like any data and we cannot change it, uh, or like it's very time consuming to change it. So this one is a little bit better. So we have like while current not equal, so like so we do current run equals current next, and then a plus plus, and then we do the same. And then we subtract, we figure out whatever is lower. We do for delta while delta is positive. We do head A equals head A next, and then we do this while head A and else we do this next one. We do delta ln B minus ln A, and then let's say it's this one gonna be delta head B equals head B next, and then we do the while head A not equal null, and or head B not equal null, we do the following: if head B, then return head A, else if head A equals, okay, if any of it will match, we'll go to the end. Head A equals head A next, and then head B equals head B, that next, and then we do the return null. That's it. We can do the like function, private function for the length. It will improve a little bit the code. So let's check it. Compile error. And so let's test this code on this example. Like we have it here, like this one. Make it smaller. Let's make it even smaller. And let's have it copy image. Let's paste it here. Okay. So so we have initially the length. Len a equals 0, current not equal null. Move the current. So len 1. We check the current not null. We move it. Len 2. We then move. Check the current not null. We do 3 and move. And then we check current not null. We do 4 and move. Check current not null. We do 5 and move. We check current not null is null. So length equals 5. In the B, then A, then B, say, have current this one. Current B not equal null, we then B equals 1. We move B. Current B not equal null, we increment B, move B. Current B not equal null, we change len B and move linter. Current B is equal null. So we have like len A5, len B3. So then we have like len A greater than len B. It means that we need to go move to len A minus len B, so like 2, 5 minus 3 equals 2. So we need to go delta, well, delta is equal to equals delta, and we do this while delta minus minus greater than 0. So we have head A, like waiting here, delta equals 2. So we check, is it greater than 0? Yes, we decrement it, and we move head. Is delta greater than 0? Yes, we decrement it, and we move. Then we check if delta is greater than 0. No, we stop. and we'll do the same for the head B if it would be len B is greater. And then while head A not null and head B not null, we check head A equals head B. No, we do head A equals head next. So head B moves there, and then head A moved there, and then what's gonna be head head B was staying there. So we have the code here. To check if we have it. We moved head B. Yeah, we move head B. Head B equals head B dot next here. So we move head B. So head B starts pointing here. We check if head A equals head B. It is. We return head A. So we return the output. Okay. So let's check this code. What if we have this example? We'll have len A, len B, len A gonna be 3, len B gonna be 2. We subtract from one from each other. We move head A pointer to the 6, and then we move 6 to 4, 1 to 5, head A and head B, and then we check if they match, and we check that before. Yep. And then they don't match, then we move head A equals null, head B equals null. We check this condition. Head A and head B. Head A was null. We immediately exit this while loop and uh, we return null. So let's go and do this. Try to figure out if that's gonna work. What I copied there. Okay, entire function. Let's check this one. Run. Submit. Yeah, still the memory is not that good. Okay, I guess it's time to check. Its time is 52nd minute. I guess it's time to check the memory here. That's even interesting. Huh. Head A equals null, head B equals null, return null. But so we kind of switch here between head A and head B. So let me try to figure out. So like we have head A here and then head B here. We what do what? We do A not equals B. No. So initially we have this A, and what we do what? Head B. If A they say basically that's very similar. That's very similar to the tortoise and the hare. The only problem, so like finding the tortoise and the hare. So in this case, we let's say we have this A and B. We move A. Do we move B after that? Yeah, we also move B. Uh, and then we move A. We move B. And then we move A. And then we move B. Okay, so like A, in this case B gonna be null. B equals null. Let's copy this one again. No, didn't want. So we have A pointer here, B pointer here, A pointer here, B pointer here, A pointer here, B pointer here, and then A pointer here, and B pointer to the null. And then we need to somehow, what we need to do that in the end. In the end. Hey, I don't want this one. This is Yaki hashtag. So head B, if B is equal null, B gonna be head A. Otherwise B next. So B becomes head A. So B becomes head A. That's very interesting. So B is here, head A. And we do. So essentially we are kind of. So this is kind of becomes running in circles. And like they say that whenever they gonna meet, two pointers gonna meet, it will mean that it's gonna be intersection point. Why they will meet at all? I wonder. I wonder why they will meet at all. Okay, let's do that. So like this is B pointer becomes here, and then we move A pointer. A pointer becomes here. So then we move B pointer again. B pointer becomes here, and then A pointer jumps to the B. So the no, it first jumps to the null, yeah? Is it? Yeah, it first jumps to the null. So the jumps to the null. And then B pointer moves here. Huh. And then A pointer will jump here, and then B pointer will jump here, and then A pointer will jump here. That's interesting. Mm, I guess this is something that I solved, but without a little bit more efficient. It looks like my last solution, but they don't have like figure out that length, that whatever. The one that completes faster, that one will go to the opposite one. Yes. So let's assume this one, that path. So this one goes like, say we have like this is len A, and this one is len B. So if first one goes, let's say, len A steps, then the second goes len B plus len B minus len A. Say this is gonna be, let's say, X, this is gonna be Y, and this is gonna be X, this is gonna be Y, and this is gonna be Z. So here like 2, oh, 1, 1, and then 3. So X3, Y1, and then that one. So you have this one, X. So the path for the first one is gonna be go like, so the second one will go 2 steps, and the first one gonna go like also 2 steps, and then this one will go like, will stay step up. So if the last one goes like len B steps, and the first one goes also len B steps. then if the one there there this one continues going len A minus len B steps, this one will go also len A minus len B steps. Um, okay, so like let's say B goes y plus z, and then A also goes y plus z, and then I cannot like get the physical meaning for that. Why they meet? If they gonna uh, reach there, when they gonna reach there? Because if the first one goes this number of steps, and then this number of steps, let's say this goes like this number of steps, and then this number of steps, then the second one, so it's like basically number of yeah, they will go the same number of I just got it. I just got it. So they will go the same number of steps. So if A goes like this one, this number of steps plus this number of steps, then the B will go so it's gonna be like 1, 2, 3, 4, and then 5, 6 steps for A, and then for the B, gonna be something like that. So the B will go this number of steps, so 2, and then 3, 4, 5, 6, and this number of steps. Okay, and B will go also 6 steps. And in this case, if they gonna go sequentially and jump to each other, like, and that's quite efficient. Yeah, if they go the same number of steps, and they jump to each other's heads, they will, if they like somewhere if they have this intersection, they will basically meet and that in that intersection. Yeah, it probably is like more formal proof, but I see that from the graph. Okay, so I'm gonna wrap up here because I solved it within like I guess 17 minutes. I provided a solution with a set submissions. Okay, so I guess I provided probably this one. No, probably like this one. So it was 90 minutes ago. Not actually 90 minutes ago. An hour ago. Okay, 16:35, and now it's like 5:33. So like almost 1 hour ago. So I got it like it's probably from the beginning. So I consider that pass, but I definitely spent some time like figure out like how many solutions I can like come up with. I came up with this one that changes the values. Then I came up with the next one that doesn't change the value, but it does some extra logic for this length, and then like doing some pre-step movements. Um, yeah, but I guess it's fine. I guess the number of steps is the same. Yeah, the number of steps is the same. So, like, um, in this case, they go at least like every node, every pointer will go to the end and then to the meeting point. And for my algorithm, I go to the end for every pointer to figure out the length, and then I go the whatever like pointer, whatever head has the more length, I go pre-calculate, I pre kind of go uh, by offset delta, and then I start like moving them simultaneously until they meet each other. So I guess it's the same kind of time complexity for the my algorithm versus this one that they suggested. Um, they suggested over here, I guess, over like here. Yes. And then if I check this one, yeah, this one is the same one. Okay, I'm gonna wrap up.